you read the actual concentration, there's a feedback loop into your ammonia injection grid that says either give us more ammonia or less ammonia. Then you go through this continuous feedback. So you always have a little bit of extra ammonia coming through the system. So you have ammonia split. This is a new thing I'm going to talk about. Oops, sorry. I don't know if I'm ahead or behind. I don't know where I am.
Go back what?
I'm correct. Now I'm back where I was talking about the CO2, which is a greenhouse gas. And typically when we controlled carbon monoxide, we would convert it with the catalytic oxidation system into carbon dioxide. Now, carbon dioxide is a regulated air pollutant. We never look at carbon monoxide versus carbon dioxide trade-offs. We still look at them as individual pollutants. Scrubbers have to have reagents. Typically you have a lime scrubber. Somebody has to produce that lime. Sometimes you have an ammonia scrubber. Sometimes you have a sodium hydroxide scrubber. Those all have their own emissions, their own power that goes into them. And then also the cost of the emissions of the actual manufacturing of the control device. Some of these catalysts that we use in some of these oxidative catalyst systems or in our SCR systems take a lot of energy and produce a lot of pollution to produce the catalyst that is then used in the control device. We don't take that into account. This is just one example of a common control device that we use for volatile organic compounds, which is called the thermos. And this is kind of a little bit of a quick schematic. You have your waste gas. You sometimes preheat it. It goes in the thermal oxidizer with auxiliary fuel, typically natural gas, but it can be propane, could be something else. Then it goes through the thermal oxidizer to the boilers and out to the stack. So while we are controlling VOCs very effectively, thermal oxidizers can control about 99%. In air pollution terms, we talk about 99.9 is 3 nines, 99.99, 4 nines. These typically will run about 2 nines to 2.5 nines. But now we're going to produce NOx, carbon monoxide, and carbon dioxide. So they're secondary. Those all should be added in when we take into account the emissions from the facility, when we look at those emissions from the control devices. Then we have to look at, as I mentioned earlier, the other pollutant pathways. If we have a wet scrubber, what are we doing with our water waste disposal? If we have a biological sulfur removal, which you don't use with hot sulfur sources, you have SO2 and it's coming out of hot stack, you aren't going to use biological, but you use it sometimes for other types of controls where you don't, it's not hot, but it produces particulate. So that's another secondary pollutant. Fly ash capture. If you have fly ash, you have bottom ash, any kind of incineration, any kind of coal burning, any of those types of things. The spent catalysts. Those oxidative catalysts don't last forever. Eventually you have to replace the catalyst. And where does that used up catalyst go? And then that leads to, again, solid waste disposal. Here's an example of a fluidized bed boiler, which is a good control device, absolutely great. But what are we looking at here? We've got bottom ash coming out that needs to go to solid waste for reclamation. We've got fly ash coming out. You're going to go through a fabric filter and then out the stack. That needs to go to some kind of solid waste, either disposal or reclamation. Fly ash now is commonly used in both two places. One is in the production of cement, but it also can be used to produce wallboard, like the wallboards in a building and a house. So fly ash actually is being more effectively used now than bottom ash. Bottom ash is not nearly as easily reclaimed. Then we look at what's going on a steam turbine and it goes on into generator power. But again, you have a cyclone systems, you have all these extra heat exchangers, all the things that go into this particular control device can be quite costly. And that doesn't include the energy to run the control device. That's just purely the waste from. Which is actually leading to my next slide, energy use of all these control devices. Energy for electrostatic precipitators, energy used for seawater scrubbers, VOC chillers. VOC chillers are extremely nice because you get your product back, but especially in a warm climate such as Singapore, you have to use a lot of energy to cool those VOC vapors down to a point they go back into a liquid form. Activated carbon regeneration. I mentioned catalyst manufacturing. Reagent production, when you have a wet scrubber and you're using either lime or sodium hydroxide, it takes energy and it takes emissions to produce the lime and sodium hydroxide to get into the scrubber to start with. Here's an example of electrostatic precipitator, and what I just want to point out real quickly here, we're looking at high voltage transformers with a great deal of high voltage wire. The energy use of an electrostatic precipitator is not small. Now, is this still the most effective control device for PM 2.5? Yes. You can take the PM10 portion of the PM 2.5 out, it gets even more effective. But for small particles, especially nanoparticles, electrostatic precipitator is still the best control device that we have. We just need to take into account the additional emissions for the power that needs to go into that particular device to see if we really have the net pollution reduction we think we have by putting an electrostatic precipitator on the back end of a stack. So this is the idea, is to take a look at all the pollutants. I've kind of bored you to death with all the details of that, but all the things to consider, add all of that together. I'm suggesting actually apply a weight factor. I'm going to talk about that a little bit more. Then evaluate the control systems as a whole. Not just take a look at the NOx controls, the SCR works, not just look at the PM 2.5 electrostatic precipitator looks, but total them all up by the weighting factors and come up with a final number and go with the set of control devices that is the lowest final number. So why would I want to add an application of a weight factor? I'm going to give you a great example right here in Singapore. Singapore has very warm climate. You guys don't have winter time inversions. And you typically have extremely low, I won't say extremely low, but low concentrations of carbon monoxide. It's not a pollutant of concern. You don't see very high concentrations. You don't see carbon monoxide levels anywhere near any of the ambient air quality standards that have been established by the World Health Organization or for other countries. Not an issue. If that's the case, why would we go ahead and put on a control for carbon monoxide or give carbon monoxide equal billing, say, with sulfur dioxide, which could lead to PM 2.5. We have higher sulfur dioxide concentrations than we do carbon monoxide. So we want to give emissions of sulfur dioxide, which leads to PM 2.5, a higher weighting than CO. We may give CO a 1 weighting. We may choose to give sulfur dioxide a 10 weighting. The other thing we might want to consider is that we don't want to produce greenhouse gases on the back end of burning our carbon monoxide. So we may give carbon monoxide a very low weighting. We may give NOx and VOCs a higher weighting because we're worried about ground level ozone. In contrast to that, if I were in the UK, for example, I couldn't give very much weighting to NOx and VOCs for ground level ozone formation. We don't get enough sunlight in the UK to cause problems with ground level ozone problems. However, they do get wintertime inversions, and they do sometimes have trouble with carbon monoxide levels. So they may give carbon monoxide a higher weighting. But that's just a way to look at those pollutants and not just assume they're all equal, but give value to them based on the particular atmosphere and air quality situation of each location. The other thing I wanted to point out just real quickly is goes much faster than I thought. I'm sorry. Is that PM, some of your particulate matter might be toxic. So you may want to give an extra point or 2 or 3 or 4 or more if particulate matter is metals, or especially if it's mercury. You may want to take some additional account into what the particulate matter is. Same with VOCs. If you've got toxics in your VOCs, you may want to give some extra points to that as well.